All right, so today we'll continue on from what we covered on Tuesday, and we'll dive into the topic of uh, instruction set architecture, or the ISA, right? You've seen this from the system skill class when we talk about the Intel x86 and how to write the assembly for Intel x86, right? Now we're gonna dive a little bit deeper into design one. Let's say I have a piece of hardware that operates on bits. How can I design a language for that hardware? So we'll learn about that today, right? So before we dive into that, we do have to review some of the material. We talk about the computer or the super high level component that you have the processor, you have the control pad and the data pad in the processor. You have the memory, that's where you store the program and the data, especially if you follow the von Neumann paradigm, which you have the program on the memory and you read the code and execute on it. And you interface with the world with the I/O, that can be the storage or input-output devices like keyboard, mouse, monitor, right? This can include things like your camera, the audio driver that's been capturing my voice so far, right? And they kind of interface with each other. And then we talk about the von Neumann model, which is called the store program computer. The key property of the von Neumann model is actually it's pretty simple. You store the program and you also put the data in the memory. And you process the instruction in a sequential pattern. You have the program counter that points to that's running right now. That's the next line I'm running. Easy, right? So you can finish the program using model. I run it line by line by line by line. I program your code, your algorithm using this concept, right? Is that the only model? No. There's another model called the data flow model, right? In the parallel and functional programming class, you are going to learn the concept of functional language. Functional language basically takes an input, computes the data whenever the inputs arrive, and process it and generate the output. The data flow model kind of maps really well with the functional language in von Neumann, you go line by line by line. Right? You have the PC point to the current instruction, run it, and go to the next line. Data flow model is different in the sense that I proceed to my program based on the availability of my data. What does it mean? It basically means that perform the operations whenever my inputs is ready. Go dig a little bit. What does that mean? Basically, I have a function. I don't care what line is that in my program if I have all my input. It can be line 1000, and the last time you run, the last line that you run is line 100. You're not running line 101. You run the function whenever it becomes ready, right? This doesn't require the instruction pointer or PC. You just need to track. Have my input arrived yet? If so, run it, produce the output for the next input. The ordering is based on what we call the data flow dependence. Think of it as a math function. That's where it maps really well with functional programming because everything becomes a math function. I have the add, I have all the inputs to my add, I generate the output right away, right? Many instructions, if you do it this way, can be executed at the same time. This means performance, parallelism. We will cover this more in the other class, but I'll show you the benefit. So the left side is von Neumann. You all see the code, right? 4 lines, really simple, doing add, multiply, add. If I tell you add takes 1 second, multiply takes 1 second, how long does it take to do this? 4 operations. 4, right? 4 seconds, and that's all. Right? Can I do better? Let's say I have a limited number of adder and multiplier. Can I do better than this? Can I finish this within less than 4 seconds? If I can do some of the adds and some of the multiply in parallel, can I finish in 3 seconds? Exactly, right? You can run the first and the second line in parallel, which is exactly this. I have A and B as an input, run the add and multiply in parallel. Then for the output of the B multiplied by 10, that goes to the third line, which is adding B with that output. And then I add the last thing because it's sequentially done. I need to wait for that until I finish, right? So this will take 3 seconds. It is faster. And it's faster, but when you write a program in C and Python, do you write in the left side way or the right side way? Do you write sequentially or is your program in a data flow pattern? How did you write your program? You write it sequentially, right? But from the conceptual point of view, you're like, hey, but data flow is better. How can we do that? You know what? Every single CPU that you buy, that are for most of them, except for some of the embedded processors that are not that powerful, right? Because some of the processors are smaller, so they can't implement this. But if you buy a CPU for your laptop, for your desktop, they actually change the way you run the code from the left side to the right side for you, right? Magically. Hardware techniques is called out of order processing, and it imitates the right side, even though you feed the program from the left side, right? How much speed up in this case from 4 seconds to 3 seconds? How much performance gain are you getting? How much performance gain do you see here? Yeah, 25%, right? So it's good. So hardware techniques, do you have to change the way you program at all? Like, do you have to somehow now everyone use functional language? Let me ask you, for those who are taking functional programming right now, which one do you prefer, sequential or functional language? Because I know people who love functional language as well, but also people who love like C and Java and Python, right? So these techniques allow you to run faster, the program become faster without the change in the way you code, right? That's pretty powerful. Any questions so far before we shift gear and start to dive into lecture, like the content of this lecture? Okay, if you're typing, I'm basically monitoring the chat as well, so feel free to hit enter whenever the question's ready. In the meantime, I'm gonna proceed toward the introductory material for the next topic, ISA, right? So I would like to ask this question. How can we talk to the computer? This computer doesn't really understand our command, right? You can't just say, add that to number, and then somehow the computer would know the language, right? And process it. That's like super advanced AI application that you have to understand. Add the two number means that I need to actually take the two number and add them together and somehow give back the results to the programmer, right? Right now, your computer only deal with electrical signal, 0 and 1. Why binary format? Anyone curious why 0 and 1? I think I asked this as system skill as well, but just to do a refresher on this. Why is it simple to do just 0 and 1? Exactly, right? That's a great answer. On and off is electrical circuits. What's the easiest thing I can tell between the difference of two things? On and off, right? I can turn off the circuit. I can turn the circuit on. I can have voltage high and voltage low, right? Yeah, except for that, we are not talking about quantum computer, not about the topic we're going to talk about for this class. Maybe if we go to the spatial topic, we might need a little bit more time on that. And it's still not measured yet. for quantum computing to be actually taking over the world, it does take a lot of really awesome research work that we have to kind of put our brain power on, right? But let's talk about the digital computer that has been around for a long time and it works too. Simple, right? On and off. That's why you can basically you build anything from 0 and 1. So let me propose this idea, right? Let's represent our human instruction that you want to add, multiply, subtract into the binary format. The command would be in binary, and the data would be in binary. Would that work? Would that work? Yeah, exactly, right? It's simple. If this is our idea, it should work. So let me ask you a different question. Let's say if I want to communicate to see you, right, in Chinese, what do I need if I don't know how to talk in Chinese? What do I need? I would need some form of translator, right? I would need a dictionary. At minimum, I need some form of dictionary that can convert the word that I want to convey into a Chinese word. That's like a minimum requirement, right? So think of the ISA as this dictionary for the language that you can speak to the computer. All right, is it much simpler and much more um kind of graspable that if I talk to the if I say ISA is something like a dictionary for you to talk to a computer, it's actually now things are more clear. I have a computer that can't talk your language. You need to program them, so you use a dictionary to tell the words, right? It's a little bit high level because there's actually quite a lot of techniques behind it, but it works for now. Let's keep that assumption, right? And this becomes the interface between your assembly code and your computer, right? Your assembly code and your computer. If you somehow can write things in assembly and you have the ISA, which is a dictionary that converts your assembly code into 0 and 1s, things would work. Now, when I said hardware, right? ISA is a language. Computer is a hardware. So there's another terminology that I had to put it here right away so that you can see the difference. When you read text or when you read like Intel chip design and say it's an Intel microarchitecture, the word microarchitecture is the hardware component. Basically, ISA define, right, the list of commands that the hardware can understand. I can put in the ISA, it should be able to add two numbers, subtract two numbers, multiply two numbers. Then what do I need to implement in the hardware? If I define in my dictionary that this computer, if they talk this ISA, it needs to be able to add, subtract, and multiply. Then what do I have to implement in the hardware? Does the hardware need to be able to add? Yeah, obviously. Yes, true. That is true. You put the logic in so that you can add the two number, right? Because you want to call the function that say add those two numbers. It means I have to build the hardware that is capable of adding two numbers. Sorry, cat attacked. And what else? Subtract, multiply, right? And let's say that's all. I never said it has to be able to do a division. Now, let me answer this question. Do I have to implement my CPU in this case to be able to divide two numbers? So let me rephrase the question. Now, in the ISA, oops, sorry. In the ISA, I have the definition for add, subtract, and multiply, right? Does the hardware need to support division? I mean, for sure, it does have to support adding, subtracting, and multiplication. But it doesn't have to support division, right? Because can you program this with the ISA to divide the two numbers? Yes, but through the add, subtract, and multiply, right? You can use like a bunch of loop and subtract and like add and multiply to do that, right? And hopefully shift and everything. But I can't call division. It just doesn't exist. I don't have that word in the language, which means, I mean, I don't have to implement that in the hardware because no one would call that. No one would call that function, right? No one would call that command, to be precise. So ISA defined the list of commands that the hardware need to understand. The microarchitecture is the hardware that allow this logic circuits to perform the command that are listed on the ISA. So your microprocessor, the CPU that you buy, is a combination of ISA and microarchitecture. ISA will tell you you can use these commands. Microarchitecture implement those commands in a way that hopefully is the fastest possible or most cost effective or use the least amount of energy or whatsoever, right? Microarchitecture is the hardware implementation of your ISA. All right, any questions so far? Okay, now we define both terminology. Let's go into the first one, ISA. What's in that, right? We talked about this in system skill already, so I'm gonna go through this really relatively quickly. If you have any questions, do let me know, please. Right? ISA need to consist of the instruction. You need to be able to tell what the computer should do, right? This includes opcode, things like addressing mode or data types, instruction types. Is it compute? Is it a jump branch? Or is this dealing with the address in the memory? It needs to have some form of dealing with register and the condition code, right? If you forgot this terminology, I do recommend to check out our system skill playlist on the x86 architecture because we do have a refresher on that. I will not do it now because we need to kind of proceed. These are the thing that hopefully you kind of can recall to some extent. I guess I should be able to tell what do I do in memory? How do I access them? Who owns what? How do I get each byte? Do I get each 4 bytes? Do I get each 8 bytes? Do I have the 4 bytes aligned? You cannot go to the third byte. You have to go to the 0th byte, 4th byte, 8th byte, or something like that. It needs to specify this. It needs to specify this so that the hardware can implement these features. It would have to just include specification on how to do virtual memory management. The topic of virtual memory we learned in system skill. Someone has to implement that in hardware. All right. So the OS and the hardware will kind of work together and manage that. What else? It needs to handle things that some of the things that you did in problem 1, right? So what happened when you send in sick kill? Oh, what happened when you want to close a program? How can you do that? How can you close a running program? Great answer. Exactly. You send a signal, right? What is a signal? It's something from the user, right? You as a user, you say, hey, stop running. I don't need you anymore. Close. What happened after you send that signal? What's supposed to happen? All right, Ghost of P1 coming back to haunt you all. What? It terminates the process, right? The process die. But think about it this way. Where's the process running at the moment? Before it died, before it died. I mean, just tell the answer. I'm sure you know the answer. Like, where is the process running on your computer? Or on the CPU, right? The CPU is like executing the code until you send the signal, say, go die, please. Okay, that sounds wrong. Sorry about that if it sounds too graphic. Please terminate the process. From the OS point of view, then what do you do? Like, what do you actually have to like send into the computer to queue the process? Okay, so let me do a recap. It sends SIGKILL, the signal to queue the process, and you can tie that to the process ID so that you don't randomly queue the wrong process, right? So you can tag, hey, I'm gonna queue that process. When you send the SIGKILL, the ISA, if you open up the x86 ISA, it will have the detailed description on what's supposed to happen when you send SIGKILL. What's supposed to happen is CPU receive that and you say, oh, okay, I just have to queue this process. It basically means that I will stop running. I will stop fetching the new program counter and run it. Gone, right? And that's it. ISA also had to specify like access control, right? The priority and privilege, so that the combination of this and the virtual memory manager can give you the such a lovely segfault when you program in C, right? And again, I know we all hate segfault, but it's there to protect the other program you're running. It also have to have the specification for the I/O and the thread management. Again, concept from P1, right? Now you can see that so many of the things that you learn from P1 and P2, the first module and second module of this class, they all have to be defined. It's defined by your ISA. Why is that the case? Because so that you can build the computer system. Imagine the world without Windows, Linux, and Mac OS. What do you do? Imagine the world without these features from the ISA that allow the OS to operate. How are you going to use the computer? Exactly, something close to that, right? You have to kind of not just speak binary, you have to kind of speak assembly, right? I mean, ISA assembly, that's fine, but you now have to write a software to manage everything you want to run, right? Because that's exactly what the OS is doing. It's a piece of software that manage the all operation of the computer, including running what program, closing what program, making sure our machine doesn't die, right? What else in the ISA is available for you? If you are working with a laptop CPU, even your desktop CPU, right? There's power and thermal management where you can turn on the fan, increase the power so that your program run faster. Anyone heard of Turbo Boost? Intel. Anyone heard about this term before? So what it does is actually Intel provide the features that increase the clock frequency so that your program run faster. What's the downside of that? Well, it does consume more power. Um, so it kicks in turbo boost whenever the driver see the benefit of running things faster. Like you run some program or games that need uh, the better performance. It does some. That depends on how you manage the driver, because sometimes you send. So the question from the chat is, the turbo boost also sometimes fight with the graphic cards. Yes and no. Basically, sometimes you send the part of the program to run on the GPU, and the graphic card would handle that, right? But when you kick in turbo boost, sometimes it maybe doesn't have to do that. You can just run some of those on the CPU side. It depends on the scheduler. So there's quite a lot of. So I don't want to go too deep into this, but there's quite a lot of components involved into determining where to run things. It's on the CPU side, the GPU side, and right now I can kind of roughly tell you that when you have a new GPU driver, there's a high chance that they would kind of like optimize for each game that you're running and tell what calls from those games should be running on the graphic cards, or which part should be done on a CPU. Right? So update your graphic driver, guys. It actually can make the performance better, unless it's non stable version, like too new. Sometimes it can also crash things. All right, example time. So let's say we have a simple CPU that can only do the following: add and multiply. Really simple. I can store a constant value in the register. I can load a value from the memory to the register, and then I can store that value. Basically, I can add, multiply. I can put a constant into my register, and then I can access the memory, read and write. Adder and multiplier take to register, and it basically write the results to the third register. You have 4 registers in total. Really, really simple CPU. And let's assume each instruction can be 16 bits long. Like it's actually 16 bits long. All right, so take this example and this specification. My first question is, how many different opcodes do I need for all these 5 instructions? How many opcodes do I need for these 5 instructions? Opcode is basically a bit pattern that tells you if I see this pattern is an add, if I see this different pattern is a multiply. I have 5 instructions. How many different patterns do I need to actually cover those 5 instructions? If you're not answering, you're thinking too hard. We need 5 of them, right? So can someone give me it can be any number. Give me a bit pattern for an add. And give me just 3 bits. Okay, let's do add is 0, 0, 1. How about the multiply? 0, 1, 0. So that's 0, 0, 2, right? 2 is 0, 1, 0. How about the let me call this instruction move. So how about the move instruction? Let's do 0, 1, 1, right? And then the load to be 1, 0, 0, and the store to be 1, 0, 1. So let's assume with this particular example so far, and these are totally correct answer, right? I can pick whatever pattern as long as it's not a duplicate. I'm fine. Okay, so now we are done with the opcode part. Now we need to specify the register ID. I have 4 register. How many bits do I need to represent all the 4 register? So let's say I have R1, R2, R3, and R4, right? I need how many bits to represent R1 to R4? 2 bits, exactly, right? I can do 0, 0, 0, 1, 1, 0, and 1, 1, right? And now for each instruction, how many registers are involved in the instruction? This one is pretty simple. I can have add and multiply the source 1, source 2, and the destination. Right? Destination is the output, source 1 is input 1, source 2 is input 2. Now over here I have source 1 and the destination. Destination is where you want to store, right? And source is the address. Over here now, the source is the address in the memory. Destination is whatever register I want to store it. And then the constant only source 1. Basically, that's the register I want to store the constant in. All right, with me so far, I need 2 bits for the register ID in my instruction. Now let's do an add and multiply instruction. Let's build the bit pattern for my add instruction first. So what's the opcode for add? Anyone remember from 2 slides ago what's the opcode for an add? 001, right? So opcode is 001. How many bits do I need for all the 3 registers that are from source 1, input 1, input 2, and output? So how many bits do I need in total? 6 bits, right? 6 bits. Source 1, source 2, and destination. How many bits did I just say that the entire instruction would be? 16, right? Instruction is 16 bits. So now there's no wrong answer here. Do you want to put this toward the left side of my 16-bit or the right side of my 16-bit? I just need one answer. There's no wrong answer here. So let's do the left side, all right? I have 16 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's say I want to do add R1, R2, and R4. What would be my instruction? What does the bit pattern would look like? So for an add, right, or an add, I want to put the opcode to the left side. So it's 0, 0, 1. Source 1. What is source 1? Actually, R1 is 0, 0 because I start with R1, R2, R3, and R4, not R0, R1. My bad. Sorry. I should have fixed that. But anyway, source 1 is 0, 0. Source 2 is 0, 1. And source 4 is 1, 1. I have these empty bits. We call this don't care. I mean, it doesn't have to be anything. It can be 0, it can be 1. I don't care. We literally call this part don't care. So if you go read the textbook and see don't care bit, yeah, it's actually I don't care what the bits are. Because is this enough information for me to tell you're supposed to do add R1, R2, and R4? Is this enough information? Oh yeah, great question. Look, that's a question of then why do we need the don't care bits? This is basically because I assume that each instruction is 16 bits. And you see in a bit why you might have need more than this number of bits. Exactly, yeah. So you already answered this. We sometime when you have a different operations, which will show you, we will use those bits. But for now, the add and the multiply, you don't care about those. So for the multiply is 0, 1, 0, right? 0, 1, 0. And then this is source 1. My bad. Let me kind of erase here. And hopefully I fight with PowerPoint and drawing. 0, 1, 0, followed by source 1, source 2, and another 2-bit destination, and then a bunch of don't care. So if I see this, I know, okay, it's a multiply between source 1 multiplied by source 2, write the result in destination. All right, now we are done with this dummy add and multiply instruction. We now have a semi-functional CPU. The next thing is, let's do a load and store, right? Load and store, if I remember correctly, the opcode is 100 and 101. We want two things. The register, right, source 1, that tells me the address. And then the destination, which tell me this is where you want to store your data. The store is the same. This is the address where you want to store. And then this is the register that holds the data. So it can be something like this load. The register, whatever is address at R1, put that data into R2. It can be store. Whatever is in R2, store that to the address where R1 is pointing. And then the rest are the big don't care. I just need to see the first 3 bits. I know, oh, it's a load. I will take 4 more bits, the source and the destination, and now I know what to do. Now I know what to do. All right, with me so far, the same logical explanation to add and multiply applies to load and store. Now let's do the last thing, the move constant value to the register ID, right? If I remember correctly, that is opcode is 011. I need one register, right? I need the destination. Now, where do I put my constant number that I want to put into this register? I have my constant, right, number. And basically, let's say this is R1. What I want to do is R1 equal constant. Sorry. So how can I represent a constant number in my instruction? Sorry, I see a long pause and I want to make sure everyone is on the same page here. So our task here, this is the last instruction we need to support, right? And I know the opcode. I know that I want to put a constant value into whatever register is in dest. How do I represent my constant number? How do I represent a number? Bits, yes. So let's say I want to put 300 into R1. I somehow need to put the value T300, right, within my instruction. Because the computer need to know from that instruction alone, there's 16 bits that you see the bit pattern. You need to know exactly, I want to put 300 into R1. So where do I put the number 300 in my instruction? I can put it here, right? I have this 5 bits. And I still have how many bits left here? 11 bits, right? This would be where you put your constant value here. if you go read the ISA, this constant, we call this the immediate. Basically, treat this as a flat number, and you can convert this to a number. All right. So let's say if I want to do R1 equal 25, right? R1 equals 25. What would be the bit pattern for this instruction? 0, 1, 1, right? So what's R1? 0, 0, R1. This is move. And what should be my constant here? The rest of the bits here. Exactly, yes. 0, 0, 0, 0, 0, 0. I think that's on 1, 0, 0, 1. Because this is exactly the value 25, right? And that's it. Now the computer know, okay, I'm going to put the value 25 into R1. Now let's put everything together. Let's put everything together. What you have is the first 3 bits becomes the opcode, right? Which can be add, multiply, the move, load, and store. Right? And then the next 2 bits become source 1. The next 2 bits can be source 2, or now the rest is immediate, or the destination. This next 2 bits become destination. And then this 3 plus 2 plus 2 plus 2, that's 7, 6, 9. So we have 7 bits left. Right. For the add is don't care for the multiply. This is still the immediate. This is don't care since this bits. And this whole thing is also don't care. Now, let me ask you this. Is this functional? Can you write a program with just these 5 instructions? This really simple as it, right? So can you write a program with this? Rephrase. Can you write a really simple program with this? Right? We can write a simple program. It seems possible. Is this a little bit restrictive? Yes, exactly. Your calculator can probably do a lot more, right? So yes, it does get a little bit restrictive. So you look at modern world ISA. The modern world ISA has so many instructions is supported, right? I just want to kind of lay out the lay of the land here that, hey, it's possible for you to design your own ISA so that when you build the hardware, it follows the design in your ISA, and then you can write a functional program with it. But then if you want to write a good ISA, then you want to make sure it kind of cover the basic command, right? And the operation of a computer that should be covered. Now, when you have the ISA, right, it basically, as I said, define what the software can do. The microarchitecture would implement these commands with some design trade-off, right? And the key things here is totally transparent from the programmer view. Programmer have no control over any of these things I listed here. Programmer has no control. So anyone want to take a guess? Why do we have this? Why do we have these techniques? Which we will learn some of this. We will learn the first one and the second one and the fourth one in this semester. But programmer has no control over this. So what's the benefit? Why do you buy new generation of the CPU? Exactly. Yes. You don't have to kind of cry over what do I do with the hardware. The hardware would optimize, hopefully optimize itself, make it fast, and when you run the program on it, it becomes faster magically. You don't need to know what has been changed in the pipeline. You don't need to know what has been changed in the memory scheduling. You don't have to know how the CPU now these days they predict what is the data you're trying to access, or whether to do 3 or 4 adds in parallel or 5 multiply in parallel, right? To make it faster. Or sometimes it actually make the computer a little bit slower to save the battery. Anyone heard of one of the lawsuits to Apple where they claim that your iPhone, when the battery reach certain amount of the battery and the lifetime, it slows down your phone. And someone's like, okay, I'm gonna sue over this because Apple somehow slowed down my phone. Yeah. So if you've heard about it before, this technique is actually a really common hardware technique called dynamic voltage frequency scaling. The reason why this is done is to make sure we use less power or more power by making it faster. Turbo boost. Turbo boost, we just talked about Intel turbo boost is kind of like the inverse of that. You boost the frequency, consume a lot more power to make your program faster. This, in this case, your phone battery is dying. So let me slow down the CPU so that it doesn't consume as much battery so it lasts an entire day. Right? So these are some of the techniques that are done by the hardware, and many programmer, to be honest, doesn't even know or aware about it, but it's done, and it's actually there to actually make your computer fast. All right. So I talk about the trade-off, right? And this is basically one of the primary design issue in most modern hardware design. What is the right trade-off, right? How many people here use floating point? A floating point number. I mean, you program in Python, right? And C. So what is a floating point number? Yeah, I mean decimal is part of it, right? But we all know this format, right? Float, something like 10.25 or something like that is a floating point format. So NVIDIA, for example, come up with a different format called TensorFloat32, which is actually misleading. It doesn't use for FP32 is kind of like IEEE standard. It's like a standard floating point format that use 32 bits. TF32 use fewer bits, but it cover the same range. What is the benefit of that? What is the benefit of that? Now you can kind of cram in multiple operations using one hardware. So we can enabling better performance. Number of register also change from ISA to another, right? x86 would have the same one set of register that you can work with. ARM ISA would have a different set of register that you can work with. Number of ports that go into the register file. Now we're going into a little bit more of a hardware. Treat ports like a, sorry, my cat was making a weird noise over there. Not sure if you heard it or not. Number of ports, treat it like an actual port, right? Where you dock the ship and use it to transfer goods and stuff, right? More ports allows you a parallel access to the register, but then it consumes more hardware components you need to use to support this. You can make the CPU faster by throwing in more transistor, right? But then it also is going to consume more power as well. Right? So it's probably not a good idea to do that a lot or aggressively on your phone, for example, right? So architecture is actually all about making the right trade-off. And also there's another issue of like, what if the ISA change, right? Because when you have a computer that works with ISA, one ISA, x86 ISA, and then I throw a program that written in ARM ISA on the Intel CPU, what would happen? It would not run. Basically, it was like it can't run. It's like if I suddenly got dropped in Japan, right? And I was talking to someone that doesn't understand English, I would freeze up. They would freeze up. We cannot communicate because it's not the same language. I can't talk in Japanese and they can't talk in English, so we are both freezing up, right? Until we learn how to talk the other language or having a translator. Compiler, in this case, if I have a new ISA, one thing I can do is to change the compiler to re-optimize for the new ISA. I can do what we call code transformation as well. There's another techniques that change the binary, the program, from one ISA into another ISA. So this is another alternative solution. But the conclusion is this: you don't need a lot of ISA, to be honest. Think of it as a human language, right? Would it be less annoying if we all speak one language? Everyone in the world suddenly speak only one language. Would it be nice? Yeah, right? Um, that would allow everyone to communicate quickly, right? And it doesn't really allow you to run into this overhead, right, of translating from one language to another. Computer has the same chain of thought, right? Would it be nice to have one ISA? But it is not always possible. That's why you have the ARM ISA. That's why you have the x86 ISA. That's why you have the RISC-V ISA. Like each one of them offer different benefits. Each one of them has trade-off. Some of the ISA has a really complex instruction like x86. Each instruction will also be specified differently, right? We see from our example, right, the toy ISA with 5 instructions. What if suddenly the world collapsed, right? And we only have that ISA? Every single programmer would cry and probably yell at us, right? Why did you come up with such a restrictive ISA, right? Each ISA also supports certain features as well, things like multi-threading. It's like basic support for the CPU, low power, low memory, right? Some of the ISA, ARM ISA also has a support for embedded device with not a lot of memory, but it's gonna be really power efficient, right? Some of the ISA support what we call very large instruction word. This is like an advanced technique called VLIW, very large instruction word. Some generation of the GPU has this, some generation of the CPU also support this. SIMD, it's kind of like the early day of the way you think about the GPU, the way it execute, it actually use the fundamental technique called SIMD, which has been around for a while. I can write an ISA to support it. I can write an ISA to support SIMD and fine-grained multi-threading at the same time, which is basically the GPU that you buy nowadays, right? There's also a different types of ISA. CISC versus RISC. Some of you might have heard about this term. CISC is called CISC because it's complex ISA. RISC is reduced ISA. Anyone want to do a guess between what's the difference between CISC and RISC? This is simple instruction. Can do basic operation, right? And for complex ISA, it support crazily complex operation. For example, x86, which is one example of the sys ISA, it does have support for moving a constant value from this address to this address in a loop. With one instruction. People who support reduced ISA or RISC people, like, why do you need to do that? I would rather use a transistor to have a bigger cache or a better CPU design for some certain aspect, because I don't have to use transistors to support those operations. People who support complex ISA would now then argue that, well, but some operations that are complex is used a lot. So maybe we should have that implemented, right? So again, this is a different type of ISA with different trade-off. And the instruction is, again, the most basic elements with the opcode and overrun. This is where I'm going to go quickly because we went through this in system skill. You can have add R0, R1, and R2, which basically means that the add is the operator, the rest are the operand. What are the other elements of the ISA? Control flow versus data flow. You can actually have the ISA that somehow support data flow and then build the hardware for that. It's actually being proposed in a few research paper, and it's quite complex to implement actually, but it can be really powerful if that's possible, right? Processing style, right? Things like number of operands. For example, you can have something like x86, right? This is basically the Intel assembly that you've seen in system skill. You can have add R1, R2. What it does is it would add R1 and R2 together and store the result in R2. To register, do the operation, store it back to one of the registers you listed. Something like a 3 operand would be like add R1 and R2 together, write the result into R3. So that's 3 address ISA. The 0 and 1 addressing machine, this was a really old style of the ISA when we don't have a lot of transistors to work with. We don't use this anymore. This is for historical context. You can have something like a stack machine where you can push, pop, add, pop, or something like that, right? Basically, everything is a stack. Accumulator is you load something from the memory and you accumulate, add, and then store it back. Trade-off, why do you have 2 address versus 3 address? Space, performance, code size. Sometimes you don't want your program to be too big because it will not fit in some processor that are, for example, the one that go into this microchip here for my AC remote, right? It doesn't have a lot of memory, so you need to have a really simple code. What else? You have opcode operands, right? You can have things like a data type. What does the bit represent? Integer, floating point, character, binary, or decimal. You can actually specify that in the ISA. You also can have a complex structure like a vector or a data structure. It's possible. You can add that in the ISA for sys ISA. You can add things that if you want to store a linked list, here's the format, right? Now that you can design the ISA, you can actually add that. Complexity of the instruction. You can add, if you want, right, an instruction to compute a convolution. Anyone here heard about tensor core? So For those of you who heard about tensor core, anyone know what is a tensor operation? It's basically sum of AI, B. It's the sum of the multiplication. It's used in many machine learning machine learning application because it's kind of like a basis of a lot of the math behind machine learning. So many hardware these days are built to perform this thing. What is this? Multiply, add, right? Basically, this is multiply. We call this multiply, add. It turns out, right, a lot of the machine learning model ended up requiring you to do a lot of multiply, add. So if you need to design a hardware, what will you do? What should you do? You know that you're gonna have to do a ton of this, a ton of like sum of AI BI. Would it make sense? And so let me rephrase the question. Would it make sense then if I built a special logic to do this sum of AI BI and call this neural processor, like basically machine learning processor? So if you've seen things like tensor processing unit, it's basically designed. It's basically designed as a special hardware that do this operation. Some multiply a bunch of two numbers together and then sum of those into one output, right? So that's a complex instruction. It's not just one add. It's not just one multiply. It's actually multiply, 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 and then add everything up, right? You can have that pre-built in the hardware, and I guess call it TPU, right? You can have simple instruction. I just say, hey, I want to support add, XOR, load, and store, and that's it. The rest, if you want to do sum of AI multiplied by BI, write a program to do that, right? Write a code to do that. So I can go both direction. It's the choice of the designer and also depending on the application, right? Or you can do the mix of the two. You can do the mix of the two. Complex operation can always be built from a simple instruction, right? So that's the trade-off between the instruction complexity, right? So if I have to support multiple complex operation, it means that first of all, right? First of all, the code, right? The code for my program is likely to be smaller, and the compiler doesn't have to do much because there's an instruction for everything, right? Basically, there is an instruction for everything. So what would be the downside here? What would be the downside against having every single instruction in the world supported? I can load 10 number to my array in one instruction. I can do finding a prime number using one instruction. I can somehow do product of prime in one instruction. What's the downside of that? What's the downside of having that in the ISA? Hardware need to implement all of these. So basically, you need to throw in a lot of transistor to implement all these things. So that's the downside of the complex instruction. And that's the benefit of a reduced instruction, right? It's the hardware is simple. It means that if I have any spare transistor, I can use it to add more cache. I can use it to add more logic to make your clock faster. You can have really, really, really high frequency clock, right? Because hardware only have to perform simple things. And then there's also room for a lot of compiler optimization as well. So you can actually analyze your code and make it fast. So that becomes a debate between RISC versus CISC. RISC, some of the anyone here play PlayStation 1 and 2? I know it's old, sorry. All right, so PlayStation 2 use MIPS. RISC-V actually it kind of evolved into RISC-V. MIPS kind of evolved into RISC-V, and is one of the really powerful RISC ISA in the world right now, right? The reason why it's powerful is it's free. So if you want to run a startup company that do like AI hardware, or I want to design an accelerator to do like cool DNA sequencing and make it programmable, I can use RISC-V ISA. Is driven by academia, by a group of researcher at multiple university, and we make it free. Basically, the community make it free so that everyone can go and take and use it and design the hardware around it. Yeah, it's open source, and you don't have to pay for the use, right? And this is simpler, right? It's simpler, so you don't need a lot of transistors to support everything. But then there's a downside, like it's just no fancy instruction. Everything is kind of broken down into a simple ALU operation, so it can be a pain to program. What's fun, I guess, what's interesting about RISC-V, this, it allows extension. So this is the part I find really cool about RISC-V. It starts with like, okay, this is the bare bone of the ISA. Simple instruction. And then if you want to add complex instruction into it, here are the remaining bit patterns that you can use, and then it would run. And you can add the extension to the ISA. CISC ISA, some of the example is x86, right, that you use nowadays, is used by both Intel and AMD. WAX, this is kind of like the extreme. We don't use this anymore because it's basically it supports way too many different instructions. You can have a fancy or complex instruction. For example, I do encourage you to look up this instruction called rep move fast. Basically, is move in a loop. You don't have to write a loop. You write one instruction, it would move, 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 move for you. But then it means that you need to have a transistor to support every single instruction that you list on the ISA. All right. So here are the trade-off. And the trade-off also opening up another arena called the semantic gap. You might have heard this terminology before. The way I would define semantic, I would go back to how you write in English. When you write a paragraph, right, that's a grammar. Whether you use the correct like subject verb agreements, you put the s at the end of the words for the verbs, for plural noun, right? So those are grammatical mistakes you can have. These are syntactic information. Syntax error. What is syntax error? Anyone here write a program and got a syntax error before? Yeah, it's like grammatical mistakes, right? And sometimes when you have syntactic error, it can be kind of odd, right? For example, if I say we is, you might be questioning, are we talking about multiple people or one person? Because the verb suggests one person. The noun, the pronoun we suggests a group of people that include myself, right? So these are syntactic error, grammar mistakes. Semantics is more like the meaning in the paragraph. If you read the whole thing, what's the meaning? So the semantic gap in this instance is basically the gap between the software that you're writing to the ISA. You can have the ISA with a large semantic gap where the instruction basically control the signal. Like remember the ENIAC, right? Where you have to plug things in to the machine to make it work, right? And then it requires a complex compiler to basically transform your program all the way to that ISA. A small semantic gap would make ISA look almost like a high-level language where you have a lot of application-specific hardware optimization, like dealing with linked lists, dealing with graph, right? And each ISA, when you translate one to another, basically you change that semantic gap, and it can be done both in hardware or in software. For example, you have anyone here use the Apple M1 or M2 processor? Anyone here? All right. So for those of you who buy the Apple MacBook that use M1 or M2 chip, can you run a program that is not designed for an ARM processor? But if you have Rosetta, right? And if you have Rosetta, what would happen when you use this software called Rosetta? Right? So you can use these tricks to actually run x86 into ARM, right? So this is the technique that people use actually. All right. There's also different trade-off. As I said, now today we're gonna discuss a bunch of trade-off, right? You can have a high-level data type like a set, a graph, a linked list, and you have the benefit of like it's making it easier to program in those if you have that in the ISA. The downside, well, semantic gap, you need to support it, right? So data type, for example, is tied to semantic level. What else are the elements of the ISA? How do you deal with memory? This is like another big chunk of the specification in the ISA. How many unique locations are in the memory? There'll be a part that belongs to the OS. There's going to be a part that belongs to each program. There'll be a part that belongs to each of the I/O, like your monitor, your keyboard, right? Addressability. Can I go access every single byte? Can I go access every single bit? Yeah, I'm sorry. There was a discussion in the chat about Rosetta. It's not running natively. Basically, you translate the x86 program so that it's runnable on ARM, right? So if the performance is not going to be the same as running it on x86 processor. So some quick exercise, don't have to do it now, but think about it. Let's say you have two 32-bit number. You want to add two 32-bit, sorry, you want to add two 32-bit numbers together, but you only have byte addressability, meaning that you only can access each byte, not the entire 32 byte. The other exercise, what about two 8-bit numbers where you have 32-bit addressability? You can't get each of the 8 bits. You only can get the entire 32 bits. There's also virtual memory support, which kind of define how you're gonna deal with virtual memory. There's the issue of big versus little endian, also discussed earlier in the system scale. What else? How many register are you gonna have? How big is the register? It's 32 bits, 64 bits, 16 bits. The benefit of register is really fast, right? So if you have more, you can store a lot of temporary data on the CPU, and that's fast. But then it also takes a room on the CPU. And register does have an evolution as well, right? If you look at x86, right, there's like RAX, RPX, RCX, and RTX. You might be curious, like some of these used to be the accumulator. It's just adding. Some of the registers accumulate plus using the address register. But nowadays, if you look at every single CPU that out in the world, every register, most of them becomes what we call general purpose register. General purpose register. It can be used for any purpose, easy to manage and manipulate, right? What else? You have addressing mode, right? It defines how do you obtain the operand. This is done in system skill already. Remember those uh like this parenthesis R1, R2, right? And then number 4, right? And then some number here like 10. There's like you take R2 multiplied by 4, add to R1, and then add 10 to it. It basically tells how do you get the address. That's called addressing mode. And each ISA would have a definition on its own addressing mode. And there's a trade-off between each of them, right? Some addressing mode will reduce the size of the instruction because you can just use one addressing mode and you know the address. Some are going to be better suited for things like array. Some type will be better suited for pointer, like a linked list, right? The downside of each addressing mode is now when you have more, the compiler that transform your program into binary need to figure out, okay, which one is the best. I have multiple options. It's a lot of searching, right? Also more work for the hardware because I need to implement every single mode here. But most of the time, these days in most modern computer, you would support more because you can cram more transistor into your chip. Right? And as I said, things like how do you deal with I/O? That's some ISA support memory map I/O, right? You can map a region of your memory to certain I/O devices, like your monitor. You can have special I/O instruction that deal with some of the special devices, like a network cards, right? You can have to, ISA have to specify things like privilege mode. I have to control, if you are not Linux, don't access this part because you're not the super user. It tells who can execute what. Exception and interrupt handling, things like secure, right? How do you handle that? Procedure to follow when something goes wrong. Procedure to follow when, say, I type on the keyboard. There's also multiple techniques that you might have seen from other classes, like vector interrupts or non-vector interrupts. These are specified by the ISA. Virtual memory as well, and address protection. If you look at classes of instruction, and sorry if I start to put yourself to sleep, we are almost done with the monologue. You can have the operate instruction. Basically, we call this compute instruction. It processes the data. Add, multiply. These are the compute instruction. You can have the data movement instruction or the load and store. This is basically instruction that allow you to interface with the memory. And then the control flow instruction, like a jump and branch, that's when you have loop in the code or if else in the code, it's translated to the control flow instruction. All right. Now, there was a question about earlier, right? Why do we need 16 bits? That's a trade-off between instruction length as well, right? Some ISA has fixed length. What is the benefit of a fixed length? Basically, assuming that every single instruction is 16 bits. What would be the benefit of me when I design the hardware if I can assume that every single instruction is, say, 16 bits? It's simple. Yes, exactly. Yes, everything on the chat is right, right? You don't have to worry about where is the end of the next instruction. If I want to run the next line in my code, I'll just grab the next 16-bit. It's guaranteed that that will be the entire thing, right? So this is easier to decode. Sorry. Easier to decode. And on top of this, modern CPU, believe it or not, you don't run one instruction at a time anymore. We would run 4 instructions at a time, 5, 6 instructions at a time. So if it's a fixed length, it's easy to grab the next 5 instructions because I know exactly how long they are, right? If I know, let's say 16 bits, the first instruction is at bit 0, whereas my second instruction, if the first instruction is at bit 0, address 0, where will be my second instruction? 16, right? At address 16, that's the second line. At address 32, that would be the third instruction. At address 48, that would be the fourth instruction, so I can go grab them all and run them in parallel. So that's a benefit of fixed length instruction. What's the downside of this? What's bad about fixed length? And you already pointed out when we go with the dummy ISA that we had earlier. What's the downside of this? It's a waste of space, right? There can be some instruction that doesn't need the whole 16 bits, but you have to have those don't care because you need to guarantee that the next instruction is in the next 16 bits. So it's a waste of space in many cases. What else? What if you run out of the whole bit pattern? You cannot extend it anymore, right? Yeah, so it's fixed. So it could overflow if you want to support more, but you don't have the room anymore. It's like, okay, done. I can't extend this ISA anymore. So it's harder to extend. And here's one of the examples. This is RISC-V. RISC-V actually offer both 16-bit format and 32-bit format, and you can kind of go and look at this, right? You see that it's always used this strict 32-bit. But then if you run out of extension, then you're screwed, right? And you have in this case, there's not a lot of unuse. If you look at this diagram, right, there's no don't here. But if you look at the detail of each instruction, some of them are not used. Like func7, for example, here, func7 for add, it's not used. It's just use IS1, IS2, and RD, right? So that's the downside. How about the variable length? Anyone remember our old friend x86? That's the variable length instruction. Because you don't even know what's the end of my current instruction. It can be 2 bytes, 3 bytes, or 4 bytes. Remember assignment 3 part 2? Anyone did that? Because I know some of you didn't do it. Whoever, when you work on that assignment 3 part 2, you notice, right? One instruction, only one instruction, can have 4 different lengths. It can be 2 bytes, 3 bytes, or 4 bytes. It's what's weird, right? So that's a variable length instruction. It allows you a much smaller code size, but then it's really hard to decode because you cannot tell how long is an instruction. For example, x86, right? Same instruction, different format. You need to first look at byte 0. You first look at the first byte, then you can tell, okay, I need 2 more bytes. I need 1 more byte, right? So that's a trade-off when you decode the instruction. When you decode the instruction, if it's fixed length, you can do what we call uniform decode, right? The same set of bits would correspond to the same thing. Bit 0 to 3 is the opcode, yay. So you just look at bit 0 to 3 and you know exactly what's the instruction. It's much easier to design the hardware with uniform decode. And it allows you to have a lot of parallelism, so you can process a lot of things in parallel. But then again, it's a waste of space. You have a lot of don't care. Non-uniform decode, like Intel x86, is more compact and it's easier to extend. But again, your hardware can be more complex. So before we leave today, we're gonna go back to what we introduced earlier, right? MIPS R4000 for our in-class exercise, which is I think only 2 of them. We'll use the MIPS R4000 for all of that. Why? It's simple. It's actually functional. PlayStation 1 and 2 use it's like the next generation of this, but it's MIPS ISA. So you know that you can actually write an actual program with this. And it's much simpler than x86 assembly. It's a RISC processor, right? And it's used commercially. It's used by PlayStation and Nintendo 64. And then the one that's used in PS2 was the next version of MIPS architecture. Most of the architecture class, at least in the US, including the one I took at CMU, right? We use MIPS as kind of like a go-to ISA because it's easier to create a design. You can look at the detail here, but we have the in-class exercise for you to deal with. So let me go to a little bit more detail with the MIPS R4000. It has 32, a lot. 32 general purpose register. They have a PC and a status register. It has a physical memory that has 3 chunks. When you deal with the in-class exercise, you see .text, .data, and stack. .text is where your program is located. Data is basically things like static array. Those are in a .data, and stack are anything that are allocated dynamically like a linked list. And the nice thing about this is there is a MIPS R4000 simulator. Basically, it simulates the actual the actual running of the ISA. You can write a program. You can write your own MIPS 4000 for program and feed this program to the simulator. It would run your code and it would actually allow you to see what's going on in all this register. The value will get updated. It will show the update for the program counter and the status that you can actually go and step like line by line by line by line. It allows you to step line by line. It allows you to run the whole thing. It allows you to load the program. It allows you to even set the value ahead of time, right? So you can actually play around with this. And you can see this is your program. And this is going to be your data. You see the change in the data when you have a load and store instruction. So in class exercise 1, please install this simulator. Go through, because you can't copy the link from here, please go to the assignments you see in class exercise, I think 18. It would basically ask you to go and install this. There's a manual here. And basically the task is write a function that adds to a number. Simple, really simple. I want you to try to run it and see the change in the hardware, because this simulator allows you to see, hey, this register get updated. Hey, interesting. In architectural research, we use simulator a lot for chip design. We basically simulate the property of new chips and show that, hey, it's faster than the old design, right? So there's a part of it that I want to kind of like experience. So please go doing that. Any question before we adjourn? I'm gonna, because we have about 20 minutes left, I'm gonna go on Discord. I think they're trying to figure out the schedule for next semester. So if they offer functional and parallel programming, definitely I think I'll come back after. So sorry, after like I just had a daughter, so so like this semester I'm so busy with like making sure making sure I know how to rest the daughter. But yeah, so we're still working on the schedule for next semester, and I hope we can resume like a typical typical schedule. And I also need to make sure the system skill is offered as well, so we will see how and why. Yes, yes, for the version, yes, please. Yeah, so if that's so I'm gonna open up for the floor for more questions. Should we just stay here or do we want to go to Discord? Up to you. Just let me know. I have until 4, so I have like 15, about 15 more minutes.